Lecture 31, Introduction to Queuing Theory. All right, we'll start off by defining queuing theory, and unsurprisingly, it is literally the theory of queues. What makes queues appear, how will they behave, and how do we make them go away? Queuing theory has surely played a role in your life, whether you know it or not. This is how tech support at Rogers, Bell, TELUS, whoever, decides how many customer service agents to have available at any given time. The answer is, of course, not enough. Because, well, they want to discourage you from calling, I think. But they do that. The local telecom chooses to minimize the number of employees because that's a cost to them. At the trade-off of that is they make you wait, and they don't really see that as a big problem because it's your problem and not their problem, right? So you can see how there's perhaps a negative incentive in that regard. With that in mind, I mean, it's not random. Queuing theory happens, and it is a study. It is a way of choosing. Queuing theory is applicable in lots of fields, though, not just when we're talking about whether a company is going to have people waiting in call centers. It's applicable in industrial design, telecom systems, computers executing transactions, and really that's the kind of thing that we're most interested in. Computers, they do things. We want them to. Okay. So, yeah, your call is important to us. Please enjoy this pan flute music for the 50th time. Right? I mean, we've all been there, I'm sure. Okay. You're maybe thinking, though, like, what does queuing theory help with? Why should I care? What does it matter here? I mean, we've talked about transaction processing, but, let's go into some more actual details about here are situations where it might be directly relevant. So here are questions that you may face when you are working on some software system, and you can answer them using queuing theory. I mean, you can guess, but if you want to have a good answer, you answer them using queuing theory. So given a choice between a single machine with speed s or n machines, each with speed s divided by n, which should we choose? Do you want one fast machine, or you have several slower machines? Obviously, you are limited in this regard. Money is sometimes a limiting factor, but we could make a decision based on queuing theory, and that would tell us whether or not we actually want one of these solutions or the other one. Number 2, if the arrival rate and service rate double, how does the mean response time change? We haven't talked about the formal definitions of the terms arrival rate, service rate, mean response time. That's okay. We will shortly, and if you know what they mean or you have a guess about what they mean, you can sort of probably guess as to whether these are important. The answer is yes, they are, but we'll certainly come back to them. Just keep this question in your mind a little bit for the future while we go through some more, and when we get to the actual definitions of terms, it'll all make sense. Third on the list, should we try to balance the load, or is that a waste of time or effort? Load balancing is one of those things that is, in fact, exactly like it sounds like, which is we sometimes have multiple servers, and workload may be unevenly distributed across those servers, and the question arises then, does it make sense to have a strategy that reassigns work from busy locations to less busy locations? It might sound intuitively like the answer to that is always yes, but we should know, I think, by now that sometimes the intuitive answer is wrong, and we want to have some data that supports that decision before we say, yeah, for sure, we should definitely do that. We should think about, what are the costs of moving things from one place to another, and sometimes it is not faster to do so. So using queuing theory, we'll be able to have a better answer, or at least a way of answering that question. Number 4, can we give priority to certain operations without harming another category of job? That is to say, if you treat all jobs equally, you get some behavior of the program, and if you say, actually, I want to give priority to things of a certain type for some reason, how does that impact the rest of the system? And that is an interesting question. Can we have a VIP lane, or would having a VIP lane make things somehow worse for everybody? You may know from many situations that actually some places don't care if having a VIP lane makes things worse for everybody because it's good for VIPs, and that's somehow perceived as desirable. But you could quantify this. You could say how much worse it makes things for everybody, if any amount at all. Next, how do job size variability and heavy-tailed workloads affect our choices of scheduling policy? So job variability, I think, is not too difficult to explain. It's just what is the variation in how long any particular work item takes to complete. But heavy-tailed workload is something where there is the possibility that they're kind of outliers. 99% of them are complete in a short time, and the last remaining 1% could take a very long time for some reason. We would say that distribution has a heavy tail because there is the possibility of these outliers that are very expensive. We'll come back to that as well when we talk about heavy tails in a later discussion. And the last question that appears on this list is, if 12 servers are sufficient to handle a rate of 9 jobs per second, does that mean we need 12,000 servers if we have an arrival rate of 9,000 jobs per second? And that one really is most likely the example that is most motivating for you in terms of why would we talk about queuing theory, because it does give us answers to questions like how many servers are we going to need if we have this much user growth over the year, right? Management says we want to double our number of users from now until July. Okay, how many servers are we going to need to support that? We can use queuing theory to actually come up with a meaningful answer to that question. So this is one way in which I think it is going to appeal, and you could sort of make a pitch to management and say, hey, we could apply some queuing theory here and get like a meaningful answer. Okay, so I like to tell stories about banks that tend to imply that I hate them. I mean, I don't really. It's a place where if I have to for some reason go into the bank, there's likely to be a queue, and I'm likely to be annoyed and thinking about how to optimize the situation. So we're going to define all of our terms now, and we will also define them in reference to a banking analogy, just to make it a little bit relatable. Pretend that you are going into a physical bank branch location for some reason. You have a good reason why you would do this. And there's no other way around it. Can't do it via video call or something. And so this is what we're going to do. And some of the terms that we're going to talk about are super obvious, but I would rather be complete than leave something out. Right. So our terms: server, the banking center fulfilling customer requests. I don't think there's really anything that I have to say about that. It's pretty straightforward. So server, the banking center fulfilling customer requests. Customer, initiator of service requests. They're the person who requests that something gets done. Wait time, the time that a customer spends waiting in line. All right. Again, super obvious. I really can't add anything to any of these, and I don't think they needed a lot of explanation. But we'll carry on. Service time. So this is the time from when a teller starts to serve a customer up to the time when the next customer is called forward. Okay, this one does actually have a little something to it in that it recognizes the fact that the customer ahead of you in line may have left before the teller is ready to call the next person forward. So they may have to do some additional paperwork. They might have to do some cleanup, something like that. So it's not necessarily as soon as the person ahead of you leaves, then you can just rush up there and it's your turn. There is perhaps some additional delay, and that's recognized in the fact that the service time includes all that extra paperwork that they do afterwards, even after the customer has left. Arrival rate. I got nothing here. The rate at which customers arrive, obviously. Service rate, the rate at which customer requests are serviced. Yep. Exciting. They're not even good definitions. Let's use the words that we are defining in the definition. It's, that's, how they're defined, at least in the book. That gives the definitions of all of these, but come on, seriously, we could do better than this if we tried. Okay. Then the ones that are a bit more interesting, utilization. So that is the fraction of the bank teller's time that's actually used handling customer requests. Assuming that they're not busy continuously, there will be some idle time, where they're just waiting for a customer to arrive. In which case, that doesn't count as active time, and so utilization in that case would be less than full, less than 100%. Queue length. The total number of customers waiting currently with the teller or both. So this one does require a little bit of explanation because it might be slightly contrary to your expectation. And that is, it's not just the people who are waiting in line, but it also includes people who are up at the counter trying to get their request done. Because ultimately, they're still waiting. They can't leave. They still need service from the bank. The service might be in progress, but it's not done, it's not over, so they gotta wait. Response time. So response time is the sum of the wait and service time for a single visit. So if you look at your watch when you go into the bank and then you look at it again when you leave, that's the amount of time that we're talking about. You might have had to wait in line a little bit, you might have had to wait in line a lot. It really depends, particularly on how busy things are, and ultimately, for some purposes, for you as the customer, you just care about how long it is before you can leave, and therefore, response time is very important. Residence time. It builds on this, and it is the total response time if the customer has to visit several times to complete a request. So you might have to do step one and then go do something else and come back later. And if that's the case, then the residence time is actually what matters. It's how much time did I spend in the bank in total today, even though I had to leave and come back, and that can happen. And then finally, there is throughput, and throughput is the rate at which customers get their requests serviced and dealt with. And all things being equal, we like having a higher throughput because, it means customers are happy and they get their requests done sooner. The bank, on the other hand, maybe has different incentives. Okay, so given all of these, here is the symbol table, which you may wish to refer back to in the future, so that you can check over at some equation that you're looking at, and you can say, aha, I know what this means. That is important. You do need to know what the symbols mean, so keep an eye on these for later. So capital S is the service time, capital V is the number of visits to a server, capital D is service demand, capital R is response time, capital R prime is the residence time, capital X is the throughput, lambda is the arrival rate, capital U, the utilization, capital W, the wait time, and capital N, the total queue length, again, including waiting and being serviced. Okay, now these kinds of things are, in real life, always a trade-off to some degree or another, and you as an individual want everything to be done as quickly as possible. You want to get to the bank, get your stuff done, get out of there immediately, and the bank could potentially accomplish that by having 50 staff members in there waiting for you at any moment, so that there would never really be any wait for any customer. On the other hand, the bank wants to minimize their staffing costs, so they're probably not going to pay people to just stand around and hope that customers will eventually show up. That seems inefficient from their point of view. I mean, they're a bank, so they're not hard up for cash. But still, they're not a jobs program. They're not a charitable organization. So they probably wouldn't do that. And I mean, if I have to wait too long to do my banking, I'm unhappy. I could take my business elsewhere. Whether or not that's likely to happen really depends. Taking your business elsewhere does require some work. You got to close the account and open the new account and so on. And there's steps to it, and it's not just as easy as like, all right, fine, next week I'm going to shop at a different grocery store, right? There's work to it, so I have to be significantly unhappy so as to be sufficiently motivated to make the change. In theory, it's a customer service business, so minimizing the wait time makes customers happy. And it would also be good if the bank trains its tellers very well so they can complete all operations in a reasonable time, even the unusual ones, quickly and efficiently, which would reduce service time. Now, this does get a little bit away from the computer world view of things. So yeah, I mean, when I talk about minimizing wait time, making the customer happy, that translates very well to the computer. But what about training its tellers well? But that comes down to, well, if you have more efficient code, it means operations get executed faster, and it means that everybody's happy because it reduces the service time by reducing the amount of time it takes to accomplish things. Overstaffed is bad for the bank. It is going to make it so they're wasting money, and the same is true for having different servers. If you have lots of servers running that you don't need, you are wasting money, and you're increasing communication costs, and that's bad. But understaffed is also bad. If there's too few people working at the bank, people really do get frustrated, and they say, you know what, I am taking my business elsewhere, and that is a bar that they have to clear. It wouldn't just happen on a whim, most likely, but it would not be impossible. And the same is true with your servers. That if your service is very slow or is overloaded because there's too many users and not enough servers, then that's bad. People will say, this service sucks. They will stop using it. They will go to a competitor. They will, leave you bad reviews. Something like that. You could save yourself that pain by choosing correctly. Okay, so queuing theory is relevant in lots of places, and the DMV is one, I think, where people really have to wait a long time. I mean, Service Ontario wait lines are bad, but I understand the DMV in California is nightmare level, and ordering pizza to the DMV is it's a strategy. I also understand in the elections there's some charity called Pizza to the Polls, where people who are waiting a long time to vote in various U.S. states are supposed to wait in line a very long time without food, and the people at the Pizza at the Polls organization are interested in having pizza delivered to them to make the wait a little bit more pleasant. I find it shocking that people have to wait that long, or even that people post on Twitter like, I only had to wait an hour to vote, and it's like, have you seen what happens in other countries? The last time I voted in the Canadian federal election, which was the most recent election at the time of recording, I think I had to wait about 10 minutes, and it was because I was in line behind a couple of people who were very elderly and taking a long time. It's not exactly supposed to be like that, so this is a sign of a problem. Okay. You have lots of queues in your computer. Some of them we know about. They're pretty explicit about it. Some of them are less obvious, but they're there nevertheless. The CPU uses some sort of time-sharing scheduler to run many programs concurrently. You have potentially a lot of different programs running on your computer at the same time. There isn't like a hard limit where the thing will say, sorry, you can't launch any more programs unless you're operating on like a shared server, ECE. Run some servers with such limits so that nobody can monopolize system resources, but if it's just your own laptop and you don't explicitly go out of your way to configure it, start 500 processes and then watch the scheduler struggle to work with them all, but it will, and there is a time-sharing scheduler to make it happen. A router. You may be watching this partly using Wi-Fi. A router has a queue for packets. Packets contain data. The queue has a maximum size. If this is exceeded, then incoming packets just get dropped. Sorry, can't handle them. That's our congestion management strategy. It might not be your favorite. You might think actually that is not ideal. But that's how it works. That's how it was designed, and that is the behavior that we see. You can think of lots of others if you want. The important thing about queuing theory is to give ourselves a formal framework for addressing these kinds of problems, for making those kinds of predictions, instead of guessing, because people are ultimately kind of bad at guessing. Okay. Let's imagine that we have a system that has one CPU that serves a queue of jobs in first-come, first-served order with an arrival rate lambda of 3 jobs per second. That is to say that every, on average, 3 jobs arrive per second. It's not the case that exactly 3 jobs arrive in each second. It's important to remember that this is an average. Every job takes some amount of time and resources, but we can, for now, ignore the particulars of it, and we can just say, these are the jobs that arrive, and we will service them as they arrive one at a time. If the service rate for this system, and it's the Greek letter mu, is 5 jobs per second, you could also state that another way in saying that the average job requires 0.2 seconds to complete. Then we can say that in this case the system is not overloaded. That although jobs arrive on average at a rate of 3 per second, they depart the system, that is, they are completed at a rate of about 5 per second, which means that our ability to complete jobs exceeds the rate at which they are arriving, meaning that we're not overloaded, we can keep up. Overloaded obviously would be the case when we can't keep up with the incoming jobs. They are arriving faster than we are able to deal with them. That's not a good situation to be in. You don't want to be in that situation, and we would like to have a system where it is not overloaded. Okay. Now, suppose that your boss tells you that the arrival rate will double. We have just signed a new contract. We're going to have twice as many users, and that means that the average rate of jobs will double. So if you do nothing, we have a problem. There will be 6 jobs on average arriving every second to a system that can service, on average, 5 jobs per second. You have been allocated some budget, and you can replace the CPU in this system with a faster one. So here's our initial system represented as a little diagram. We have lambda equals 3 as the arrival rate into this queue, the queue being that little sort of sideways bucket with vertical lines, and it's first come, first served. And our CPU has mu equals 5, which is to say it can complete an average of 5 jobs per second. And so if lambda will double, by how much should mu increase? Our objective is that the customer should not notice the increase in arrival rate. That is, the customer should not be negatively affected by this change in any way. All right, so the question that I'll ask you is, do we, number 1, double the CPU speed? Number 2, more than double the CPU speed? Or number 3, less than double the CPU speed? I'll let you think about it for a second before I unveil the answer. All right, the answer to that is, well, we don't need to double the CPU speed. We can see later in formal terms why this is the case, but if we just think about it for a minute, if we double the service rate and double the arrival rate, we actually get half the mean response time. Mean response time is something that we've talked about, the expected value of t, so it's e, and then in square brackets the letter t. And I mean, if we go back to the system, right, if we say that we double the power of the CPU, so mu is now 10, that means that we can complete 10 jobs per second, or about one job every 0.1 seconds. Again, keeping in mind all of these figures are averages. And this being the case, it really means that if we doubled the CPU speed, we would complete jobs a lot faster. And so having the capability of completing 10 jobs per second when we have, say, only 6 of them arriving, we are staying way ahead of where we need to be, and we're completing jobs a lot faster. But if the goal is just to make it so that users don't notice any problem, all we have to do is keep up with the arrival rate of 6 jobs per second. We don't have to go all the way to 10. And if that is so, then we don't need to double the CPU speed. We just need an increase, and it doesn't have to be quite that big. Okay, here's an alternate scenario. The kind of system that we have previously talked about is what we call an open system. An open system is one in which jobs arrive independently of completion. So jobs arrive at random and not dependent on any other. In this alternate scenario, example 2, there are always n equals 6 jobs running at a time. And as soon as a job completes, a new one is started, and that's what makes it a closed system. So you have a backlog of 500 million transactions to analyze, and you set a certain level of parallelism. You say, all right, n equals 6, and so we're going to process 6 of them at a time. Maybe we have a 6-core CPU. And then every time you complete one, that's the trigger for a new one to start. So as soon as a work item is finished, start the next one, and dispatch it and send it to the queue. That's what makes it a closed system. We'll talk more about the difference between a closed and open system soon. If you're still not sure about it, well, don't worry, we'll get there. So we have 2 servers, and each job that goes through will be processed on one of them, each of which completes, on average, 1 job in every 3 seconds. So here's our closed system, right? We have a splitter at the input that sends half the jobs to server 1 and half of them to server 2, each of which has its own little queue. Each server has a completion rate of 1/3, which is to say that it takes about 3 seconds to complete a job on average. And then as soon as one of the jobs is complete, that's the trigger to send a new one into the queue. And that's why there is a line that connects the output and input, thus indicating here a closed system. Okay, so the bad news is that sometimes improvements do nothing. If in that scenario we replace one server with another one that is twice as fast, so it completes 2 jobs in 3 seconds, does that help? The answer is no, not really. Why is that the case? Well, because half the jobs get sent to server 1 and half of the jobs get sent to server 2, so we're not done for the day until all jobs have been completed. So even if server 1 is finished after, say, 4 hours, and it still takes server 2 8 hours to complete its half, the total completion time is still 8 hours. So nobody's really happy in that regard, right? We didn't solve anything. We didn't speed up overall completion time because we have a rule here that says half the jobs are sent to server 1 and half of them are sent to server 2. And server 2 is the slow one, it is the bottleneck, and it is unchanged. So that doesn't help. Does raising n in this scenario help? By increasing the amount of jobs that we have sort of in flight at a time? No. The bottleneck device still remains the limiting factor. Having 10 jobs in flight, but still half of them are done by the slow server, doesn't help. Strangely, dropping n to 1 might actually help because that makes a difference, but it's not improvement because you're only using one of the 2 servers at a time. But then having one of the 2 servers be faster would be better because instead of taking 16 hours, it now takes 12 hours. But we still made it worse overall. So nope, that's not an improvement. But if it is an open system where arrivals are independent of completion, then Actually, it's the opposite. That speeding up one of the two servers actually makes a big difference. Because then requests can arrive whenever, and we can get some of them done faster, and everybody's kind of happy with that. And there's no concept of, well, we have this huge amount of work to do, and it's done when it's done. It's just we are always receiving incoming requests when they happen to occur, and we respond to them, and we get them done. And sometimes the user is happy because they get it done faster, and sometimes it's the normal speed, and they're not unhappy, but it's okay. And that's the big difference between an open system and a closed system, is whether there is a relationship between the arrival time and the completion. In an open system, jobs arrive whenever. This is, you are a user, and I don't know, you go look at Waterloo Works, refresh the page, see if there's anything to do. That submits a request, and your job, what you asked for, show me jobs. That's independent of anybody else doing the same thing, assuming you're not like getting together with your friends and saying, all right, at exactly 12:01, we're going to refresh. You probably don't do that most of the time. But in a closed system, then you get the scenario where actually these things are not independent at all, and as soon as one job is completed, the next one is started. So batch processing of work, for example. If you were a TA making an auto grader where it grades a student's assignment, and as soon as that's done, it submits the next one to the queue, that would be a closed system. Third example. Do you want one fast server or n slow ones? Horse-sized duck and duck-sized horses jokes aside, incidentally, duck-sized horses, I'm pretty sure, is the correct answer. You can divide and conquer a lot better. I suspect a horse-sized duck. Keep in mind, a horse is about 500 kilograms for an average horse. I don't think I would want to fight a duck that was 500 kilograms. Let's say that. Now, what's better if we want to optimize the mean response time when we have non-preemptible jobs? That is to say, once a job has been started, it has to run to completion and cannot be interrupted. The answer is, it depends. A big factor is, what is the variability of job sizes? If you're at the grocery store, and you find that a lot of people have a small number of items, 12 items or fewer, and there's one guy who's buying one of everything in the store. You don't want to be standing in line. You just came for milk and eggs, and you're standing behind a guy who has an overflowing shopping cart because, I don't know, he's planning for the apocalypse for some reason. What if we run out of beans? That kind of thing. You don't want to be in line behind that person because, at the grocery store, there are many different checkout counters, and once somebody gets started in checking out, you can't really interrupt them. That's not an option. You can't preempt them. So if there is high variability, as there is when there is a grocery store, then you actually probably want to have multiple servers, because you can just choose a different lane and not get in line behind the person who's shopping, as though this is the last day on which there will ever be anything for sale in this store. And it would be just faster for you to go to the express lane. You want 2 items, please and thank you. On the other hand, if the system is not very busy, load is low, then chances are you might actually prefer one fast server instead of a whole bunch of servers that are hanging around doing nothing most of the time. If there aren't very many concurrent requests, there's no need to have 4 servers waiting around when, on average, you have only 1 request at a time or 0 requests at a time, in which case you could save some money by not running all of those servers. And then if the other caveat is if jobs can be interrupted. So if you can put something on pause and come back to it later, then in that case you could always use a single fast machine to simulate n slow machines. So the single fast machine is at least as good as the alternative. So yeah, we're going to find that it's frustrating, but this is Sparta, or at least real life, that a lot of the times the answers for queuing theory is it depends, and you have to get into the specifics of the work that you are doing so that you know whether or not a chosen strategy is going to work well or whether a proposed change is going to work well. You have to get into the details, and unfortunately there's rarely any hard and fast rules where you can say, yes, more servers is always better. That's just the disappointing reality